accurate. What can you do? I'm assuming that there are no software bugs. I'm assuming all your implementation is right. I'm assuming that you have not forgotten to do something, or you've not you don't have an extra tab in your Python code or something like that. So assume that all your code is right and your classifier is still only 75% accurate, and you have exhausted. This is you've exhausted what you can do with just hyperparameter selection and such things. So, what would you do? Any ideas based on what we've seen all the way through? Yeah.
Look at feature selection or transformation.
Look at feature selection or transformation. That's one good idea. Anything else? Yes.
Build an ensemble.
Build an ensemble. That's another good idea. Yeah.
Retrain this mirror image of the
So then we are hoping that what would that give you?
that there could be features when you take a mirror image of an input. There could be features which are only extracted or learned by the high weighted nodes. It would have been when you initially trained it.
So what do you mean by mirror image here?
Like an upside down image. You have,
Oh, you mean I see. So you're talking about image classification.
yeah.
Okay. I had to kind of figure out the context. Yeah, image classification. So basically, you want to perturb the inputs. You want to perturb the inputs and kind of make the classifier more robust. So that's a good idea, and it's increasingly becoming more interesting and popular in the research world lately. So at some point when I thought about this, I thought, what's the lowest hanging fruit? Nobody told me that I mentioned this, but the first thing that you would do if you're in Google or something is ask for more training data. You can always, Google has infinite money and infinite compute. You can always buy more data, or you can always get users to give you more data. So you can somehow get more training data. You could change the features, like someone mentioned. You could use more features, less features, or other features. You could change how you do training. You could, perhaps run your algorithm for more iterations. Maybe you can use a different learning algorithm. Maybe your hypothesis space itself is wrong and you should have used something more expressive, say like an ensemble. Or maybe you need to play with regularization a bit. You need to do something that's non-standard with regularization. So there are a lot of things you can try. And the problem is, it can be very tedious. There are dependencies between these things. If you do things in a certain order, one thing may break, one thing may not, and so on. And it seems to rely on luck. Maybe if you try you use a different classifier with the same features, you get the right answer, but depending on the day of the week, you don't. So really, the problem is not so much what you can do, but the way to think about it is, how do you do diagnosis? So you need to think about diagnosis of machine learning. And if you know where the problem is, you can actually start using solutions that target the problem rather than knowing trying everything out. Some possible problems could be things like your model is overfitting the data, meaning you have a highly expressive classifier that essentially remembers the training set. As a result, the generalization performance is bad. This is basically high variance. Another possibility is your model is underfitting the data, which means your hypothesis space is not good enough to represent the concept. How do you detect underfitting or high bias, basically? Maybe your learning is not converging yet. Maybe you're stopping the learning algorithm too soon, perhaps because you have a deadline. You need to finish it, and you have only 3 more hours to run the thing, and you need to get things up. Or perhaps that 75% that you got is not the right thing to measure. If you're measuring the wrong thing, anything can look good or bad. It doesn't really matter. So we need to, you need to think about all these things. So let's just go through these in order. Just to remind you, overfitting is a problem that comes up all the time. It's when, the crudest version of this is when the training error is way less than the test error, or if you want to talk in terms of accuracies, the training accuracy is much higher than the test accuracy. Essentially, what's happening is you have a system, you have a model, your learning algorithm has converged on a classifier that explains the training set very well. but pretty much only does that. Underfitting is when both training and test accuracies are unacceptably low. It means even the best classifier that you have is not good enough because the hypothesis space that you've chosen itself is not good enough. It's not good enough, it's not expressive enough to represent the content. Both of these can be bad. How do you detect over or underfitting? One useful strategy is to plot the training error with increasing amounts of training data. So you have a data set, you plot the training error with increasing amounts of training data. At the beginning, the error is going to be low. Why would the error be low at the beginning? And it seems like as you add more data, the training error is going up. Can someone comment on that? And by the way, this is nowhere close to real data, the real plot. I plotted this in PowerPoint. So it's about as bad as it can get. So, but it's possible that this could happen. Your training error is really, really low when you have a very small amount of training data. Imagine you have only one example. You have one example and your classifier is 100% accurate on the training set. You had a hand up.
Is there a philosophical answer to this? I could try one.
Go for it.
I think it's following the rule that the more you know about something, the more confused you are.
That is too philosophical for this early in the morning. But maybe you're right because I'm unable to process it. So let's give you the benefit of doubt and say yes. The answer that I've been thinking about is way more mundane. You have only one example. You don't need too much capacity for the classifier to remember it. So it will remember that. If you have only one example and it predicts, and the label is positive, the classifier would say, yeah, predict everything's positive. So, it's easy to kind of get high training accuracy or low training error with very, very few training examples. But as the number of training examples grows, the classifier kind of settles into what might be thought of as the error in the data, the underlying noise in the data, and it gets an accuracy that is 1 minus the noise in the data. But of course, this plot by itself is meaningless. Did you have this plot by itself is meaningless. What we need is a generalization error, and of course, when you have very little training data, the generalization error can be pretty bad if your concept is not something exceedingly simple. So what you see is as the amount of training data grows, the generalization error keeps dropping. Okay, and this is kind of easy to explain because you see more data, so you are able to generalize better. However, there could be a problem. What if there's a huge gap between the training error and the generalization error? By generalization error, I mean something like validation or test error. So, as the amount of data grows, let's say the gap never really shrinks. There's always this big gap. What that suggests, this by the way, is an example of high variance or overfitting. What that suggests is that you're exploring a class of models that seems to always do better on the training data than in the future examples, no matter how much data there is. Which means your classifier is extremely, or your hypothesis space is extremely rich, extremely expressive. As a result, it just remembers the data no matter how much data you give it. Okay, so this is a sign of overfitting, and by the way, this is all kind of impressionistic. I'm not talking about any concrete numbers here. I'm not saying that the gap should be more than some number or some less than some number. This is something that you plot and eyeball. So this is something that's useful to detect overfitting, and if you want to think about it from a software engineering point of view, you could build software tools that does this automatically for you. That given if you want to build a machine learning infrastructure system, take some data, it trains overnight, it trains all these models and does everything, and then when you go to work in the morning, you have this plot and you're like, I have to try again. So this is something useful. Let's look at the other extreme. But before that, are there any questions about this kind of plot? And by the way, today's lecture is not necessarily heavy in math or any math, but it will be heavy in intuition if you want. And so I want you to kind of think about the math that we saw, but I won't be talking about the math directly. Another case is when you have underfitting. In underfitting, what you might see is it seems like they converge. It seems like generalization error and training error seem to meet, which means that maybe your classifier is has gotten as good as it gets. But both of these are unacceptably high. If the converged error of the best classifier, even with a lot of data, is unacceptable, that means even your best classifier, even in its strongest situation, namely where you have a lot of data, even your best classifier has lousy generalization. That means you have to rethink whether your hypothesis space itself is good. Maybe your hypothesis space is not expressive enough, and it does not. There's no hope, basically, this space, right? So this is the same curve can be used for kind of detecting, in some sense, whether you're over or underfitting. What can you do then? Let's say you've detected overfitting or underfitting. Some of these things that I listed earlier can help with these ideas. If you are underfitting, usually adding more features could help. When I say more features, I don't mean more random features. I mean more, informative features. You need to think about the problem. Adding fewer features could help with overfitting because you are essentially reducing the expressiveness of your classifier. So removing some features could remove the possibility that your learning algorithm finds mere correlations with noise because there's lesser noise. Of course, if you use other features, you can do both. Something that I see now, this should also be there should be something there. If you use a different hypothesis space, you could, play with overfitting or control for overfitting or underfitting by changing the hypothesis space. If you have overfitting, you know that your hypothesis space is too expressive, so you want to somehow reduce it, make it smaller. Maybe you don't want a 150-layer neural network when you have 3 training examples. Likewise, if you have underfitting, maybe you need to make your classifier more expressive. Maybe you need feature transformations that can introduce more expressiveness, or maybe you need a deeper neural network. One way or another, you want a class of functions that can express more. Likewise, you could play with regularization. Maybe over-regularization leads to underfitting. Under-regularization leads to overfitting. Because over-regularization means you are ignoring the training data a lot. Even if you have a lot of data, regularization, heavily regularized classifiers would say the regularizer is more important. In the SVM, for example, the C would be very, very small. That means there is a lot of data, but it's underweighted. So maybe playing with a regularizer could help with overfitting or underfitting. Any questions? Not, we're going to march on. Let's now look at this situation where your learning algorithm your learning does not converge. And I mentioned that you should have automatic. If any software that you build, any infrastructure around machine learning that you build should plot those learning curves. You should plot another learning curve, which is something like this. Most algorithms that we saw in the semester are of the form where you minimize some sort of objective, some regularizer plus loss or something like that, even perceptron, for example. What you would do is, you're minimizing some function. You know that the value of the function should go down as learning proceeds. So an obvious thing to track is the value of that function that you're optimizing, the loss function. Sorry, not the loss, the entire objective for SVM. It would be something like half W transpose W plus sum over the entire data plus, and there's a C somewhere. Or something like that. That's the objective that you're optimizing, so you should plot it. And this is like mandatory. You need to plot the objective because that will tell you whether you converge. So if you plot the objective and you need to go down the objective surface, if you want to think of it that way, it's somewhat intuitive to see that the learning has not converged in this point, because as the number of iterations grows, it's still the objective is still going down. But it's safe to say that the learning has converged in that region. It's kind of flat. It's important to plot this because this will tell you when something like this is happening. Learning has not converged here because it's still dropping, but what about here? It seems like it's decreasing, but not by much, and this is like an uncomfortable situation where you might have to run your learning for longer because it's not converged a lot more. Or you could decide, I don't care about convergence. The objective function that I'm minimizing is only a surrogate for the true error that I really care about. So simultaneously, you could also plot something like accuracy on the validation set, which would be going up here, and then maybe it's flattened out. So you could stop learning here. So this is accuracy on validation set. So both these curves need to be plotted, and you need to kind of look at both of them and decide when learning is done. Yes?
I get that we need to predict accuracy on a validation set, but when we're tracking an objective function, is that also on a validation set?
No, this is objective on the training set. This is the function that is actually being minimized. So the blue line is on the training set, and the red line is on the validation set. And another thing that I would recommend is anytime you use any sort of learning, set up your system so that you automatically plot this. Because I can tell you that this has saved me from a lot of debugging. Just eyeballing this curve has told me that maybe there's a bug in the code that I did not know about. And I don't know, this does not reveal the bug. Tell you where the bug is, but it tells you there's a bug. For example, if you see something like this, and you need to go down, you know that the function you are minimizing, the contract is it is minimizing something, the value should not go up. So this is a kind of objective function that is not really good. So we are doing stochastic gradient descent, and it seems like the value is going up here. So clearly something's not right. One caveat though is while this helps to debug, if you're doing stochastic gradient descent, the objective function will kind of wiggle down a bit. It won't have such massive jumps, but it might look something like say, something like that. There will be minor upticks, but not like massive jumps like this. The guarantees for learning with gradient-based methods only apply to convex functions, so they apply to linear models. But in practice, it seems like the same is true also for functions that are not convex, in particular neural networks. In practice, the learning curves for neural networks also should look something like this. So it's important that you plot this. What would plotting this get you? It tells you when you have maybe you should use a different algorithm, or maybe you need to use. It's not about the model, but it's a statement about the algorithm. It's about the convergence and the fact that maybe your algorithm is not good enough. Maybe you need simple stochastic gradient descent is not converging fast enough, and you need to use one of these fancy variants that are out there. Like I mentioned in the class, maybe last lecture, something that is popular today is called Adam, and it seems to be used quite a bit. And one of the reasons is there are very efficient implementations, and it's also efficient from the optimization point of view. So maybe you need to use Adam. Maybe you need to use another algorithm, say AdaGrad or something like that. So that could be an answer. Questions?
You said it'd be helpful also plot that other validation line.
Yeah.
Is that our main test set, or would that be another?
Never on the main test set. Never on the main test set. In fact, I tend to be a little bit more conservative with respect to even looking at the test set. What I tell my students is the day you start your project, once you split your data into train and test and validation, you zip the test file, you compress it, and you don't uncompress it till like the day before the deadline, or maybe a week before the deadline to account for software debugging time and all that. But don't even look at the test set, because looking at the test set could mean you have contaminated the model through your head. You looked at it and you realized, oh, in the test set, this feature seems to be important. And as a result, your classifier won't generalize. So I'm actually terrified of the possibility that we have statistical models that are tuned on the test set, because we'll get to that later. Increasingly important decisions are being left to statistical systems. And how can you trust them if they are, if their construction is used not to arrive at a statistical truth, but to build somebody's career? Because if you get accuracy of 85%, you get a raise. Okay, let me fit the test set. So that's dangerous. Other questions? Maybe one thing that you should always be asking, and you should ask this no matter whether your classifier works or not, is maybe you're not measuring the right thing. You should always ask whether what you are evaluating is really the correct thing for the application that you have. Maybe accuracy is not the right thing. Your homework, the data set that you have for your homework, your class projects, your exploratory projects that you're working on have the property where the data is extremely skewed. And so accuracy is a meaningless thing, and claiming 99.9% accuracy is useless if 1 in a million examples are negative. So when you have unbalanced data, maybe you need to measure precision and recall and measure and mistakes. If you're doing regression, I don't even know what accuracy means if you're doing regression. You need to measure something like squared error or something else. So you need to know what to measure, because otherwise I don't know what's going on. And this the decision of what needs to be measured should be driven not by your learning algorithm, but by the application, but by the context in which the learning system is going to get used. So, for example, if your classifier is being used to guide medical doctors in their decision-making process, it's not clear whether just accuracy is a good enough thing. Maybe there is a higher level measurement in terms of the number of lives saved, for example. So be creative with your measurement, and especially be careful not to tie the measurement to the objective that you're minimizing too directly. For example, just getting down to the bottom of that objective function should not be the thing that you measure. Some papers have seen and rejected papers where the paper reports, look, we got this value of objective function at convergence. This is our objective value, so our method is better. But you invented the objective function. Who cares what the objective is? I mean, it's the application that should decide. In fact, an extreme version of this could be, you need to decide what to measure before you decide how to train. And that way you have committed to a certain kind of evaluation even before you've committed to the algorithm and the models, because the evaluation should be decided by the context of the machine learning system. That makes sense? So let me talk about error analysis, unless there are questions.
So this is stepping back a little bit. One of the things you talked about, I think it was last lecture, when you're doing the cross-validation,
right,
is making sure that the data sets, your folds all have the properties.
That's right.
So when you've got a bunch of data and you've got test, train, validation, are you doing that same sort of?
That's right.
And then if you're doing that, how are you making sure that you're not contaminating your test data in a situation like that?
So what I tend to do is I have code that does stratified this sort of splitting.
Okay.
And that code does not know about the data where it's going to get used.
Okay.
I use that code for everything. So I mean, well, now I don't use it for anything because my students do it. But I've written this code once and I've never seen it afterwards. And it's been the same thing that I use every time. And also I try not to even look at, the only thing I confirm before committing to the test set is to make sure that the label distribution is the same or is similar. So that otherwise I'm artificially introducing a bias into the test set that did not exist during training. So I do get that specific. And I think that's fair because you're not looking at the data, you're looking at an aggregate of the data that you already had anyway. But yes, that's a good point. I mean, always question any software that looks too deeply into the test set. Other questions? Let me now talk about error analysis, because error analysis is a different kind of a thing than just diagnostics of learning algorithm errors. In the class, you've been looking of, this is the machine learning code and machine learning ideas have been front and center. This is a machine learning class, so of course, everything's machine learning. But if you actually implement this stuff and you deploy it, turns out it's a tiny part of the whole thing. This picture is from a pretty cool paper from a conference that from this year on is going to call New IPS for all sorts of really good reasons. The machine learning stuff that we saw is a tiny part of a big application that includes data manipulation, data wrangling, data management, and then it's situated inside the legacy code that might actually be running inside some company's systems and being served to customers maybe or one way or another, and then there's some monitoring that's going on that keeps track of whether everything's broken. The point is this, it may seem like this is a huge deal, but the way I think about it, it's probably the heart of a massive amount of software that this has to fit inside. And let's say that you train a classifier, you deploy it, and you put it into this, massive system, and things are not working. And now you need to know where the errors are and how do you make this better in such a context. And there might be problems. Maybe the feature extraction itself is buggy. Maybe the feature extraction itself is noisy. Maybe you transform your data in interesting ways, and along the way, the data gets, the signal gets lost, or signal gets manipulated some way. It's important to keep track of how much error is introduced in each of these steps. And this is really what is often called error analysis or a relative study, where you try to explain why a system is not working perfectly. And this typically involves a lot of manual labor. So let me give you an example. The example I'm going to use is from a typical kind of text processing function, where we have text, like say a document if you want, like your the exploratory project, for example, is kind of is an example of this. The input that you never maybe actually it's available to you, but maybe not all of you saw. The input is movie reviews. It's text. Movie reviews, from a computer's point of view, is just a string. So we need to classify strings. But of course, you don't leave it that. You convert it to words. So there is a data transformation already, and perhaps that's noisy. And maybe another transformation could be you look at the text and the words, and you identify parts of speech. You identify what's a noun, what's a verb, and such things. Maybe you want to do something more fancy. Maybe you want to use a parse tree. A parse tree says very crudely identifies what's the subject and object of each verb. And then all of these are not part of your machine learning code. All of these are somebody else's stuff. And what you actually implement is going to depend on all these transformations and the original data, and you have a machine learning based application. And maybe this doesn't work. But perhaps everything that you did inside this box is fantastic, but the problems lie elsewhere. So how do you detect it? It's entirely possible that each of these upstream modules, if you want to think about it, are themselves the output of machine learning systems that you don't get to control. These are statistical systems. For example, you can use the Stanford part of speech typing or the Stanford parser. You're not going to change it because it's its own thing. Each of these could be error prone, and so we need to account for we need to somehow understand where the error in the system is so that you can kind of fix it if necessary. rather than just asking where the error is, because I believe the error is probably everywhere, you need to identify how much each of these things contribute to the error. A very useful thing to do is to replace each component with ground truth. Where do you get ground truth? It's hard labor. You manually draw the trees, you manually do these things. You have some data set where you take this component and replace it with ground truth. You don't use this noisy thing. You take this component and you use a noisy thing. For example, you can use an example would be, let's say the end-to-end system gets only 55% accuracy, but when you plug out the predicted, say, word, the first one, and replace with ground truth, you get 60. When you take out the predicted parts of speech and use ground truth, you get 84. This is a big jump. And then adding ground truth trees gives you 89, and then of course adding ground truth output gives you 100, because you know the ground truth output, what's that to predict. Which means the problem is not in your part of what you designed and spent a lot of time thinking about, but in somewhere inside the context, the input that came in the form of parts of speech. So now that suggests that you should get a better part of speech type. So the component that hurts the most is the part of speech. So you need to change that. And this sort of ablative study, this is typically called an ablative study, a feature ablation, where you want to explain the difference between a stronger model and a weaker model by understanding which removing what makes the model weak, or adding what makes the model strong. And you can even think of this in terms of features. Let's say you have invented a lot of features, and you want to understand which feature is most important. So what you should do is, swap out some, remove some features, train the model. Remove another group of features, train the model, and the one that helps the most, the one that changes the system, the performance the most, is the one that's most important. The higher level point here is you should never think that it's just enough to have a classifier that works. That was the focus of this class, because that's the stuff that you need to learn. But when you apply this stuff, and I hope you do, you should not just focus on the classifier working. If a classifier works and you have no clue why it works, you must feel uncomfortable. Because it might be that the classifier works because you're accidentally leaking the ground truth information into the model. Or maybe it's working for all the wrong reasons, and we'll get to that later. Understanding why models work helps you, interpret the predictions. It helps you debug things, and it also provides this sort of a audit trail. Let's say your classifier decides whether somebody should get a loan or not, and it denies the loan application, and somebody comes to you and is like, okay, you are the guy who denied the loan application. Tell me. And you can't say that, feature number 8000 was 17, and that's why it got denied. You need an interpretable system, and this is an important research question today. And it's increasingly important. And there's, for example, DARPA, the Department of Defense Research Wing, has a huge project called Explainable AI, which basically focuses on this question. How do we build machine learning systems that can explain their answers? People can do that, right? I mean, if you show me a picture and ask me why is there a cat, I can point to part of the picture and say, oh, there's the furry bits. How do we get classifiers that can do that? Let's talk about how we can inject machine learning into, I say your favorite task, but then I know what's coming next. Let's say you have to classify whether a fish is salmon or tuna. Definitely not my favorite task, maybe it's yours. How do you go about this? There are very, very crudely two kinds of approaches that seem to be prevalent. You can think of the slow approach, where you spend a lot of time thinking, you identify the best features, you spend more time thinking, you identify the best algorithms, the best everything, you implement it, and that's it. Hope it works. You may end up inventing a new learning algorithm, you may inventing a new way of thinking about learning for this problem, and this may take a lot of time. The advantage is this kind of approach leads to new insights, maybe even new learning algorithms, and this is the kind of stuff that you would see more in research. There's also the iterative approach or hacker's approach if you want. You implement something, you do that, you use all these diagnostics methods that I spoke about today to see whether it works. You come up with some decisions to improve it. You iteratively keep improving it. And you see this more in the industry, it leads to faster release. You have something that kind of works and then you can get more data using that and such things. You see this, for example, in Google a lot or Facebook, where you just release something and then the process of releasing it gets you more data. And that gives you, more signal to improve. Both of these are good, both of these are bad. You don't want to prematurely optimize your system to something and spend maybe 3 years working on something and then realize, everything that you did was not good. Or you don't want to commit to a certain path and then you just go along that path and then you realize that you didn't think it through. So I'm not sure, the slide says classifying fish, but really what I'm talking about is, there is a higher, somewhat more profound thing, which is think about what you're doing rather than just trying out something. What to think about? You should always think about whether you have the right evaluation. Maybe you have the right evaluation, but your loss function has nothing to do with it. Be wary of data contamination. Be terrified of data contamination. Your test set should never even have any hint of the training set, because learning is not memorization. Learning is generalization. It's not enough to get good results on your training set. You should not see the test set either, and I spoke about that. A simple thing that can lead to perfect accuracy is you have a feature whose value is the label. That can lead to perfect training accuracy because it doesn't take too much to just copy a label from one of the features. It may seem like a silly thing that should never happen, but it happens way more often than I would like to admit. So just be extremely suspicious if you have a classifier that's perfect. It's almost not true that there is any data set that is perfect. So be very, if I see a classifier that is 100% accurate, my immediate concerns are maybe you have a feature that's equal to the label. And as a result, of course, you get 100% accuracy. Or maybe you contaminated the training set with the test set. Or maybe you're not measuring the right thing. But I truly do not believe that there's a classifier that's 100% accurate. Be aware of the trade-off between underfitting and overfitting, or the bias variance trade-off, because it does show up a lot and you should be prepared to change things. We didn't get to talk about this because of dimensionality, but intuitions that may work in low dimensional spaces in 2 dimensions or 3 dimensions, proof by pictures, for example, don't really translate to million dimensions. Not necessarily. Sometimes they do, sometimes they don't. So if you want to prove something, don't prove it with pictures, prove it with math, prove it with algebra. Try not to rely on these kind of gut feeling intuitions too much. Some people have made entire careers out of that, and I respect their gut. But most people somehow stumble at some point, so just be wary of that. Speaking of theory, maybe a theoretical guarantee is only theory. Most theoretical guarantees involve some assumptions. If the data is linearly separable, then I have an algorithm that can find the perfect linear separator. If you have a good algorithm, I don't know. Depends on whether the data is linearly separable. So maybe the assumptions that the theorems make are not only true if you have infinite data, or if you run your algorithm for infinite time. We don't have either of those, so maybe things don't work. For a famous example of 2 examples. A classifier that is perfect with infinite data is 1 nearest neighbors. Right? If you have all data, then of course you're going to be perfect, because any new point that comes in, you find the nearest neighbor itself. So it's perfect. So it's kind of a useless thing. Another example is a classifier, a learning algorithm, stochastic gradient descent. The guarantees for stochastic gradient descent, the guarantees of convergence for stochastic gradient descent are really available only when you run it to convergence. When you run it to infinity, but in practice that doesn't seem to matter. So there's something that's something that's not something that's missing. Which is why you need to have experiments on real data. It's not just enough to show that, hey, look, I have a fantastic algorithm and I have this theorem and I'm done. You need to have your assumptions grounded in reality. But big data is just not always enough. More data is always better, but clean data is even better. But keep in mind that most of our learning is based on label data, and we may have a lot of data, but we may not have a lot of label data. So if you want to think of imagine building a classifier that decides whether a rock on Mars has water in it or has ice in it, and try to collect a billion training examples for that. It could be hard. So maybe it may be possible to get billions of images from Mars, but it may be harder to get billion training examples with labels. So it's not just enough to have big data. What we need is a lot of label data. It's not just enough to have just data. You need to have some sort of knowledge to guide your learning. Remember that learning is essentially impossible if you don't have some sort of inductive bias. What that means is if you don't have some assumption about the hypothesis, if you don't make some assumption about limiting this hypothesis, because if you are going to search over all functions, it's just not possible to get, it's computationally not possible. You might end up overfitting, for example. Learning requires knowledge of all kinds. When I say learning requires knowledge of all kinds, that seems like a profound statement. What I mean is using machine learning in practice requires some knowledge about the domain that you're working in. It's not magic. I mean, if there is one lesson that I want you to take from this class, there is no magic here. It's just, working. Working as in you doing the work. So you need to have some knowledge that comes in. What kind of knowledge? When you decide that 6-layer neural networks are the right thing to use, you have introduced knowledge. When you decide that a decision stump of depth no more than 15 is the right thing to do, you have introduced knowledge. When you decide linear classifiers are the right thing to do, you've introduced knowledge. When you choose certain features, you've introduced knowledge. Knowledge comes into play at every step. When you choose a certain learning algorithm, maybe the choice of the learning algorithm is not good because maybe the learning algorithm comes with some assumptions that are violated, very clearly violated in the data. Maybe it doesn't matter. If it does not matter, you should go in knowing that it doesn't matter. It should not be something that you just throw and hope it works. If you're going to use this kind of stuff in real life, be prepared to spend a lot more time than you like on feature engineering. Most students who take this class and then go work in the industry come back and tell me, yeah, we spent a lot of time talking about algorithms, and then I did an internship and I spent 2.5 months out of 3 feature engineering, and then I ran some algorithms. Why didn't you tell me about feature engineering? Because it depends on the domain. I can't tell you how to feature engineer a classifier for rocks on Mars in a systematic way, the same way you might feature engineer, say, document features. So it's something that's intrinsic to the domain, and that's why it comes back to knowledge. So once again, there is no magic. One thing that you should know is, if you have the perfect features, if you have exactly all the right features that were used to define the model, then your classifier should be fantastic. All of these things, the choice of learning algorithm, the choice of the hypothesis space, the choice of features, you should think of it as, statements about your assumptions, actually, about the nature of the problem. If you decide that 16-layer neural networks are the right thing to use for classifying image, handwritten digits, then you're saying that that's the amount of complexity there is in handwritten digits. If you're saying that these features are important, you're saying that's the amount the problem is characterized by these features. So all of these are, statements about the nature of the problem. In miscellaneous advice that I couldn't put into a different slide. always try simple things first. There's no reason to spend a week training and then realizing that maybe a decision stump of size 1 is good enough. There's no reason to try the latest and the greatest thing, and there's no shame in using simpler models. There's no reason to try fancy neural networks that you may hear about on a problem that does not need it. So if you should, any sort of schematic study that you use machine learning for, you should always use simple things first because they form at least a baseline. And maybe they're good enough that you don't need to try the more difficult things. So always you try simple things. Occam's razor is an important guiding philosophy. That said, ensembles always seem to work well. It's one of those annoying things where you try a lot of stuff and then you just ensemble them and it always gives you 2% improvement. It's like sriracha sauce, it makes everything better. You should always think about whether your problem is learnable at all. Maybe you've been tasked with a problem that is unlearnable. There is no signal in the data that you have. Keep in mind, learning is generalization. It's not just running these algorithms, it is generalization. So, and I'll give you an example of an unlearnable problem. I'll create a data set, a binary classification data set, where I have some features. I know all the features, there's no noise in the features. They're perfect. And the labels are generated by tossing a coin. So, the labels have no correlation to the features. Why would you expect that thing to be learnable? Just think about it. And maybe machine learning is not always the solution. This may seem like contradictory advice coming from a class called machine learning. But maybe machine learning is not always a solution just because there are, there's someone trying to throw money at a problem for machine learning doesn't mean that machine learning is the solution. Try to solve the problem, not just be, don't have pet techniques that you always want to use, don't have hammers that you want to use everywhere, try to solve problems. Okay, any questions about any of these things? These are all random pieces of advice that I just want you to keep in mind now that you have all the powers in the world. Yeah.
Is there any intuition, I guess, that you've developed over which methods to ensemble? Like in the homework, right, we did decision trees and I learned on those. So could I learn from a separate linear classifier? Is there any subset that was well in your?
Not necessarily, no. So what I typically, bear in mind that there's a certain amount of laziness that guides my decision making. So I just tend to use voting because that does roughly as well as something, the incremental pain that you have to go through to make the other things work sometimes makes it not work. These days, if I want an ensemble, I just use a neural network. And I still vote on top of that, but it's still often it's voting of all sorts of things. There's some amount of one of my implicit biases that I always have when I use any of these things is I am extremely leery of very complex things. So I try to use simpler things because if I have a system that I cannot explain, I don't believe I have a system. So I want not just to have something that seems to work, but also something whose properties I can point to and say, look, it works because of this. So I try to stay away from extremely complex things. With that said, though, I'm starting to warm up to using neural networks and deep neural networks because they work so astoundingly well. And that opens up a new class of research questions. How do you explain it? But most of the time, this is my first principle in everything. I prefer simplicity. I mean, that may seem like a grandiose thing. Maybe it's because I'm lazy. Okay, now I'm going to step things up, to a higher level a bit and talk about making machine learning matter in the real world. Many of you were at a talk that Kiri Baxter gave earlier this year. She had this really awesome talk at ICML. ICML is one of the two big conferences in machine learning. She had this awesome talk at ICML, I think 2012, a keynote where she talked about, we should not be just building CAD detectors and handwriting detectors and such things. We should be thinking about how machine learning can matter in the real world. And she had these set of challenges to the broader machine learning community. These are really, NASA kind of problems. These are, what do you call them? Moonshot problems, if you want. For example, can we have a human life saved through diagnosis or intervention that machine learning has initiated, or maybe some legal decisions that result based on machine learning analysis that leads to interesting problems and ethical issues, which I'll get to in a bit. But I want you to not just think about the applications. I mean, there's a whole bunch of you that are seniors and you're going to be graduating and such things. When you're graduating, I don't want you to just go out there and start using data science because it's there. Give yourself moonshots and see if it works. In order for these kind of things to work, you also need to be aware that machine learning involves huge amounts of software. Some of you, all of you in your homeworks are already starting to hopefully get aware of that, but that's only the small, you're only scratching the surface here. There's huge amounts of software, and there's this idea of technical debt, where you try something and it works, and you just stop cleaning it up, and you accumulate garbage code over the years, and after maybe 15 years, you have some code that you don't want to add an extra space to because things will break. There's this very nice paper that talks about machine learning as a high-interest credit card of technical debt. Check it out. Actually, it's worth reading and it's worth digesting that advice. But there are other problems. These are problems for software engineers, and software engineers are only a small part of mankind. I would argue an important part, but still they are only software engineers. I think we are entering a phase in our existence where machine learning and data-driven decision making is going to be extremely important. It's increasingly prevalent. The algorithms that we see in the class, even the algorithms that we see in the class are no longer just proof of concept. These are algorithms that are being used for making important decisions that affect people's lives. So, a really, really important question that we need to all think about is: are our algorithms biased? Are they discriminatory? How do we ensure that our algorithms that make decisions about people's lives have transparency? When should you believe your model? Should you believe it at all, in fact? Should you actually leave all decision making to it, like autonomous driving, for example? Maybe you have all these tools. We have looked at tools in the class. We have looked at ideas that are just seem to be, enveloped in mathematics, and probability and such things. But these are tools that are going to get used for bigger things. And just like any tool, it could be used for ethically dubious reasons. So if you find yourself in a situation where you have to do that, you should be aware of it. These are all, importantly, thing to keep in mind is all of these are not criteria that are reflected in loss functions that we optimize. These are all auxiliary criteria for success that the loss function does not even know about or does not even care about. And how do we optimize these things? Examples of biased classifiers. What if classifiers are used to decide whether somebody should be sentenced or how long somebody should, whether somebody should be given parole from jail, or whether classifiers are used to decide whether somebody's loan application is rejected or not, or classifiers are used to decide whom to fire. These may seem like terrifying examples, especially now that you've looked at the insides of classifiers and you know how bad they could be, but these are all real examples. These are actually happening today, and it's a bit scary if you think about it, right? Your classifier has an accuracy of 70% and it decides to fire somebody. And it's like the lottery. Important questions, and I would argue these are research questions that we should, as computer scientists, as people who understand machine learning, questions that we should think about is how do we ensure that classifiers don't exhibit discriminatory practices? You can look up infinite examples of these online. How do you ensure that classifiers are fair? We need, to build some framework that can somehow deal with the situation that the underlying data itself is unfair. If data is collected from the real world and the real world is unfair, the data would be unfair. Does this mean that the classifier should be unfair, and is that a justifiable thing? I have no answers to this. I want you to think about these questions because I expect that you will be working on these things. We have the right to explanation. In fact, the right to explanation is codified in the new European Union's GDPR, the General Data Protection Regulations. For example, let's say you have a job and the classifier decides to fire you. It turned out that the classifier decided to fire you, but you were an instance where the classifier made a mistake. How do you go to court and claim that this was a mistake? What we need is statistical methods that not just make predictions, but also can explain the predictions. There is some transparency. We need algorithms that can explain. We need frameworks to even build algorithms that can explain. We don't have the beginning of the mathematical tools for these things. So again, if you want to have a successful research career, solve one of these things, and maybe you'll get a paper, a PhD, or you'll be famous or infamous, depending on how you solve it. It turns out machine learning and data science is one place where computer science people can actually talk to humanities. There is increasing work that talks about machine learning and data science and the legal field. Maybe we need to rethink or refine maybe how our laws exist, how our legal systems make decisions. It's possible to build statistical models that can very, very efficiently create what looks like real evidence. These are things, if you want to use the language of the class, you can define generative models. Remember generative models, which are probability of X and Y together. You can build generative models and sample from the generative model, from the probability distribution, to create videos that look like people are doing what they do not. If you want an example of that, look up this example of Barack Obama talking about interesting stuff. How do you deal with that? I mean, the legal profession needs to kind of be aware of that, and some of you may have maybe working on that stuff. What if Tesla's autopilot kills somebody? Who's to blame? Is Tesla to blame? Is the owner to blame? Is the programmer to blame? Or let's just blame the person who died. What if, and even worse thing is, what if an autonomous weapon decides by itself, with no human intervention, to kill somebody? There are autonomous weapons out there today. So who has liability? These are important decisions that, if you think about it, our loss functions that we minimize are nowhere close to even being, forget asking the question, nowhere even close to, we don't have the language to ask the question that codifies these things. So the point I want to make is this is an important area. This is an area that there is we're starting to see some work, and people are flailing around to even define things about, say, what 30 years ago now, the idea of learning was similarly such a vague concept. I mean, learning seems like, what does learning mean? You read a book and you learn. Until people came along and codified the idea mathematically, and that led us to developing interesting tools that are robust and all that. So the theory of learnability gave rise to this whole thing, and maybe there is room for theory of fairness, or theory of accountability, or transparency, and all of these are algorithmic fairness, algorithmic accountability, algorithmic transparency. This is fairness, accountability, transparency. This is FAT ML or FAT Star or FAT Conference. If you're interested, check out those links and you'll find some interesting stuff. But even without the theory, I want you to be aware of these concerns at every step along the way when you use these ideas, when you use when you define a task, and write a definition, when you collect data, when you define features, when you define evaluations, when you decide what algorithms to use, basically all at every step along the way, you need to be aware of these concerns because some classifiers may be used in situations where you did not intend them to be or in ways that you don't want them to be, and you need to be aware of that. So this is just my tirade on how we need to be more responsible citizens, but that's actually important and that's probably more important than getting a grade. Very brief summary in 10 minutes of the entire semester. Let's see if I can do it. The first lecture we saw that learning is a system is supposed to learn with experience if performance, according to some well-defined performance criteria, improves as experience improves. Pretty much most of the time in the class, when we talk about experience, we talk about the size of the data set, but perhaps experience could be defined in other ways. Under this kind of a scheme, we saw many different models. When I say model, I mean what kind of functions the learning algorithm uses. By the way, these are the same slides I used in the first lecture, and I promised in the first lecture that by the end of the semester, you should understand all these words, and I hope you do. We saw many different models. We saw linear classifiers, we saw decision trees, we saw ensemble, non-linear classifiers, and neural networks and such things. These are all just kinds of functions that we decide to learn. There are different learning protocols that you should be aware of. For most of the semester, we looked at supervised learning. Supervised learning is where we have training data and we do something with it. We have labeled data and we do something with it. But that's not the only kind of learning that exists. There's unsupervised learning where we are just given examples and we are asked to discover patterns inside it. Typically, this comes under the umbrella of clustering or data mining. In semi-supervised learning, it's like this happy intersection of both these worlds where we have some labeled data but tons of unlabeled data, and the question is, can we do more with that? We saw many different kinds of learning algorithms, or many different learning algorithms, but they can be broadly categorized into two big buckets. Online algorithms look at one example at a time, make a decision, update the internal state, and throw out the example. And this can be used in streaming settings, for example. Batch algorithms, the learner has access to the entire data, and we looked at many different algorithms under this bucket of batch algorithms, where you have the entire data, you can do whatever you want to do, you can go through the data multiple times if you want. Today's successful algorithms are mostly batch algorithms, not because they are inherently better or worse, but because they are more convenient. We often have the data that we want and we just use it. The underlying question that becomes extremely important is how do we represent data? There is maybe, let me risk a conjecture. If you have the right representation, learning becomes trivial. Learning becomes unnecessary because the perfect representation for is the hypothesis itself. If I give you the classifier, why do you need to learn? So the this tension between finding the right representation and learning is always there, and it manifests itself in the form of features or in the form of neural architectures. We didn't talk about dimensionality reduction. Some of you hopefully will encounter it elsewhere, or maybe have already encountered it. If not, take a look at it. It's a useful set of techniques to kind of clean up data and get better representation. All of what we saw was built around the theory of machine learning. And this provided this sort of a framework from using which we explored all these ideas. The question that we kept asking was, what does learning mean? We can define learning as not making mistakes as we see more data, and that gives us online learning. We can define learning as probably getting the right classifier or probably getting a good enough classifier, and that gives us packed learning. We can define learning as getting a classifier that is most probable given the data, and that gives us Bayesian learning. And all of these are just frameworks for defining what learning is, and all of these give rise to algorithms. And you can kind of, the nice thing is, there's this interplay between representation and how you optimize and how you evaluate. This is a table from a paper by Pedro Domingos. We probably saw some of these things. We saw nearest neighbors. We saw support vector machines. We saw these things. We saw these. We never saw rules. Unfortunately, you don't see too many classes teaching about teaching learning rules these days because it's unfashionable. But it used to be the thing maybe 10, 20 years ago. Machine learning classes would have an entire section dedicated to learning logic programs. We saw some neural networks. We really did not see much graphical models. Hopefully, some of you will encounter that in AI. There are many, many different ways in which we can evaluate. So accuracy, precision recall, but there are other things. We saw no optimization really. We pretty much were in this box here, but there are other algorithms. In fact, most of what we saw was a special case of that, which was stochastic gradient descent. But you should be aware that there are other algorithms as well. Yeah.
Does optimization mean optimizing like your accuracy and not like the runtime?
Yes, optimizing mathematics. Yes, not optimizing for time, but optimizing the loss functions or something like that. Yes, we totally sidestep the question of optimizing for time. Perhaps there's an entire class on how to optimize machine learning for time. I think that would be cool, actually. But there are these three big components that kind of interplay, and we saw all of these things. I would argue that machine learning is really easy. No, seriously. It's a remarkably diverse collection of ideas, all of these things. But there is an underlying unification that seems to come up all the time. You start off with what looks like a very, very different assumption, like minimizing loss and such things, and maximizing the likelihood and such things, and you work the math and it comes back to loss minimization. You start off with perceptron and as an algorithm, not as any optimization, just as an algorithm, and it turns out it could have been derived using this loss minimization framework. There seems to be a remarkable unification of ideas. You start off with naive Bayes, and it turns out the hyperplane, it's a hyperplane. The same ideas keep coming back again and again. I would argue that machine learning is almost too easy because in practice, a lot of these ideas work roughly equally well, and it's the intellectual lineage of these ideas that sets them apart. So, in practice, maybe all you need to do is use the classifier that you have the code for. We did not see so much. In fact, I was talking to another faculty the other day. Maybe there's room for a machine learning 2 class, which might cover things like kernels, which I mentioned this in my class in one of the lectures before. It's my utter disappointment that we have not covered kernels in class. We've not touched upon unsupervised learning and more complex classifiers like hidden Markov models or multi-class topic models and stuff, and structured models and such things. But what we did see is the tools, the intellectual tools you need to think about these things, and hopefully you'll be able to pick up these topics by you know how to kind of reason about these topics. Of course, there are other classes that follow. We have data mining and clustering. Sometimes we have theory of machine learning. There are various applications that you can go to. Then you can go. We are in data science. It's important to understand data visualization. You can specialize based on the kinds of classifiers that we're learning, like the models or structured models and such things. These are just CS classes, but then you can go beyond. You can go learn about math. Optimization is extremely important. Philosophy, even if you want. The entire course was focused on the foundations, the underlying assumptions and the concepts and the algorithm ideas that we keep encountering again and again. It's not about using scikit-learn. It's not about using TensorFlow, but hopefully you should be able to pick these things up because now you know what those functions mean. And more importantly, as my student just discovered yesterday, there are bugs in these systems, and you might be able to identify them. What we did see is like a broad understanding of both the theory and practice of machine learning, of different kinds of machine learning. You hopefully have the ability to now implement algorithms, and if you want to make a career out of that, that would be cool. And at a higher level, what we kind of touched upon, but not directly, is the kind of problems that machine learning should be applicable, and how to make the appropriate choices and how to not make the right choices. So my hope is that you use the material you saw in this class for things that I can possibly not dream about, because all of you are from there's such a diversity of backgrounds and such a diversity of people in the class that it would be awesome if you do things that I cannot imagine. In a good way, in a good way. Anyway, so that brings me to the end. I probably timed it perfectly. So that's the last lecture. Thank you for the class. It's been a privilege.
What's that?